Hello and welcome to the first in the series of Codility training videos. I don't know, I just kind of thought it would be a fun thing to go through and offer you guys some more advanced solutions to coding challenges, starting with a simple advanced coding challenge. This one is called TapeEquilibrium, I believe. So what we're doing here is we've got a non-empty array consisting of integers. So representing numbers on a tape. We can take this tape, we can split it into two pieces. And each piece is going to be the first chunk that's split at that point compared to the next chunk that's split at that point. So for example, if we have some kind of array like this, we can split it in many different ways. We could split it such that only 3 is on one side and all the rest 10 are on the other, and we find the difference of these numbers. We could split it so it's 4 and 9, and we get 5. And what we want to find is what is going to give us the minimum difference that can be achieved. Okay, so the reason I picked this problem is because there's a way to do it that's not going to be a good way, but we're going to pseudocode for a second and discuss the way to do it in not a good way. We can go and counter through all these, so we have I is in range length of this kind of thing. And then we can take, the sum of each part. So A from I to, or from, I guess, the start to I. And we can take A from I until the end. And then we take sort of the difference of these two and take the absolute value of that. So, and we go through and we set the min difference equal to the lesser of the min difference or the result. Right? So basically, this has got a lot of problems with it. We're going through the loop completely, so we have this O(n) complexity of time, which is then compounded into what I think is essentially n squared time complexity, because we're going to then take each part. Yeah, so it's n squared time complexity because we're cycling through it once, and then we're cycling through it twice because we're taking the absolute value of this big chunk of the sum of this, I should say, the sum of this, and that's going to take forever. O squared time complexity, no good. So what can we do? We're going to do something that's called a running sum or running tally, and that's going to help us out here. So let's say running sum is equal to that, and we're going to do this in one sweep instead of a sweep which is exponential. So we're going to go over the array. And first we take out our edge case. Running sum is equal to 0. Then we're just going to add that number. So the first number just gets added to this array. All right. Okay. But if it's not 0, then what we're going to do is we're going to add it to the array, but as well as the previous number. So we're going to add, let's see, so append yes, plus like so. That should do it. Okay, and now just to make sure I haven't lost my marbles, I'm going to go and print and check what we've got here. So, all right, first number is 3, 3. And then we get a 1 here, and it adds to that, so it's 4. The second number, we add 2, so we get 6. 4, we get 10. 3, we get 13. All right, great. So we've got a successful running sum. This keeps track of the sum of all the numbers up until that point. So now that we've got this, a little aside. This isn't necessary, but in a way it kind of is. We're going to refactor this. This is not really a function of the solution. We want it to be a function of producing a running sum. So quickly we'll just take all this and take it out of the main function. All right, let's see that it still works. Oop. Let's see. What have I done? Doesn't like that it's the same name. Perhaps. Just see. Yep, that's good. Okay, so it's working still, and now we have our running sum right there. Now, how does that help us? Well, we're not cycling through the thing and splitting up each sum anymore. We can get to these differences with simple arithmetic instead. So, we've gone through once. We're going to go through the running sum. All right. And now we're just going to look at the data a little bit and see how to get it from here to there. So, okay. So 3 minus 10, well, so 3 is going to be the first number. Oops. Silly, silly. There we go. Okay, so 3. Well, we've got the first number, we've got the second number, all good. The only thing is we don't want it to go all the way to the end. So let's clear this out actually, because we want it to not do this 13. We only want it to do up to the 10. 13 minus 0 is always going to be too large. So basically, the last one minus nothing, is never going to be the minimum distance. Okay, 3, 4, 6, 10. 3, 4, 6, 10. Very good. Now, what's the other factor? Well, the other factor is actually, let's look at it. It's the 13 minus this one. So let's do the last digit minus, let's see what we got. Perfect. 3, 10, 4, 9, 6, 7, 10, 3. Excellent. All right. So now all we really need to do is find the difference between these two and take the absolute value of those. 7517. 7517. All right. Very good. So we're going to take a minimum difference and we're going to set it to a very high number. Let's say like that. Keeping in mind that the range of each element is not that high, so we could even get away with less than that. But it doesn't matter. So if the absolute value of this is less than the min difference, we want to set the min difference to this. So actually, we will name this another variable, do a little substitution, like so. All right. Return the min difference. Great. So what have we done here? Well, we're only passing through once on the array to make a running sum, and then we're passing through once again through the running sum array. So it's basically at worst 2n time complexity, which is way better than n squared time complexity, where it was going through, and each iteration that it would go through, it would then also go through entirely each one again. So this is going to be a lot faster and a lot better. Now let's look at it for a second, because, you know, we got plenty of time left. Plenty of time. We're going to think about it for a sec, because we have arrays that can be 2. Let's see what happens with this test case. Yeah, looks good. We have an array that could be 1,000 up to -1,000 to 1,000. That's also good. 1,500, so -1,000 plus 500. It's -500, 1,000. Yep. Yep. Okay, that looks good. Yeah. I'm missing any edge cases. This is where they really want to see you go to town in the interviews, is on the edge cases. And sometimes they're sneaky, and you're under a lot of stress in the middle of the interview, and you're like, oh, I don't know about edge cases. But you just want to take a breath. You figured out the main part of the function. Think about it for a sec. Am I missing any special circumstances? Integer in the range. It's 100,000. Yeah, if it's 100,000, it shouldn't be any different. I'm not going to put in a 100,000 thing array. That's a little excessive. But it shouldn't have any impact. So each element of its array is an integer at the range negative. Yeah. Okay. I'm going to say that this is complete. Yeah. And see what happens. Ta-da! 100%. Okay, so this really was testing to see whether we can reduce the amount of time complexity of a problem. And you always want to be keeping an eye out for that. Anytime that you're doing something with a nested loop kind of structure, you really want to beware, because it'll take a huge amount of time for the computer to do. And so in this case, we were able to reduce it to, let's see what they say, ON complexity, and we got 100%. All right, I hope you found this educational or informational. Have a good day.